The title of the paper is FaultRideThrough Strategies for Grid-Tied and Grid-Forming Smart Transformers Suited for Island and Interconnected Operations. And it will be presented by, as I said, Mr. Justino Rodrigues. He was born in 1985, Penafiel, Portugal. He received a master's degree in electrical and computing engineering in 2010 in the field of power system. He is an I&D researcher at Inesc since 2010 in the field of power systems with a special interest in power electronics, renewable energy sources, and distributed energy resources integrations in power systems and power hardware in the loop. He is currently pursuing a PhD in sustainable energy systems, focused on the exploitation of smart transformer concept to implement innovative control strategies to operate hybrid AC-DC distribution systems. The authors have asked to present a video, to have a video presentation of their paper. So I ask the video to be played, please.
Do you have the video with you?
No, I haven't, but
okay.
The host will present the video.
Okay. The sound is not playing.
I haven't heard the sound as well.
Yes, yes.
Hello everybody, thank you for attending this presentation about the paper named FaultRideThrough Strategies for Grid-Tied and Grid-Forming Smart Transformers, suited for islanding and interconnected operation. This presentation is divided as follows: context and motivation, developed computational models, proposed FaultRideThrough strategies, simulation results, and finally, conclusions and future developments. This work is motivated by the envisioning that distribution networks are expected to accommodate large portions of renewable energy sources, electric vehicles, and energy storage systems. In this paradigm, improvements in controllability and observability of distribution networks are required. In this scope, Smart Transformer is a possible solution for enable additional controllability and observability in distribution networks. It is based on the solid-state transformer concept, which opens the door for advanced monitoring and control functionalities. Besides that, it provides DC-link connectivity, which enables the formation of hybrid AC-DC networks, highly available to connect DC resources. However, in comparison with the traditional low-frequency magnetic transformer, the smart transformer has no inherent fault-right-through capabilities. Although the inclusion of these capabilities in power electronic devices is widely addressed in the literature, its incorporation in smart transformers remains largely unexplored. The smart transformer has the unique characteristic of having a distribution network derived from it. Thus, fault-right-through capabilities envisioned for smart transformers must be suited to mitigate adverse impacts of voltage sags in the smart transformer's distribution grid, as well to ensure continuity of service in smart transformer's distribution grid in face of fault disturbances in the upstream system. In this scope, the purpose of this work is to propose fault-right-through strategies for smart transformers. There are two case studies addressed in this work, chosen to the particular challenges they pose. The first case study evaluates the provision of fault-right-through in a grid-tied smart transformer with all local energy storage capacity available, using the proposed strategy. The second case study evaluates the provision of fault-right-through in a grid-forming smart transformer which is supposed to support an unplanned islanding of a small section of the medium voltage AC grid where the smart transformer is connected without power supply interruption and moments after the start of a fault disturbance in the upstream system. In order to evaluate the proposed fault ride-through strategies, computational models for the smart transformers were developed. It is not intended to make a detailed description of those models in this presentation. Both smart transformers are constituted by three main elements: the medium voltage inverter, the isolated DC-DC converter, and the low voltage inverter. The same model for the isolated DC-DC converter was used in both smart transformers. The same approach was adopted regarding the low voltage inverter. The main difference is at the level of the medium voltage inverter. In the grid-tied smart transformer, the medium voltage inverter is tied to the upstream system voltage, controlling its output current, while the medium voltage inverter of the grid-forming smart transformer controls the frequency and magnitude of its output voltage. Now follows a description of the proposed fault ride-through strategies, which are the focus of his work. The fault ride-through strategy for the grid-tied smart transformer constitutes an additional control layer acting on the controllers of the low voltage inverter and isolated DC-DC converter, as illustrated in this slide. Since no local energy storage capacity is available, the proposed fault ride-through strategy exploits the voltage sensitivity in the hybrid AC-DC distribution network to regulate its net active power. The hybrid distribution network considered for this end was modeled according to the diagram presented. It comprises PV generation, EV charging, and miscellaneous loads. The strategy itself is constituted by three control structures. The feed-forward control provides a fast reaction to voltage sags. Its output is calculated as a function of the AC voltage measured in the medium voltage inverter. The current limit violation control is focused in removing any steady-state current limit violation in the medium voltage inverter. Its output is calculated as a function of the output current in the medium voltage inverter. Finally, the transferred power maximization aims to minimize the active power curtailment in the hybrid distribution network. Its goal is to compensate for excessive activation by the two previous control structures. The fault ride-through strategy for the grid-forming smart transformer is based on a different approach. It is located in the control structure of the medium voltage inverter, namely in the current limiter block. The rationale consists of controlling the voltage drop in the inductance of the coupling LC filter of the medium voltage inverter. It exploits the fact that current of the medium voltage inverter is determined by the voltage drop in the inductance of the coupling filter. Since the grid-forming smart transformer has a local energy storage system, it relies to assure the power balance in the smart transformer. There is no need for direct intervention on it to provide fault ride-through. The strategy itself is composed by three control structures. The voltage phase compensator acts on the phase shift of voltage drop in the coupling inductor. This regulates the active component of the voltage magnitude compensator acts on the magnitude of the voltage drop in the coupling inductance. This regulates the reactive component of the output current. The virtual impedance complements the action of the voltage phase compensator and the voltage magnitude compensator in the first moments after the occurrence of a voltage step. rising or falling. It enhances the activation speed of the proposed strategy in this most critical instance. In order to evaluate the effectiveness of the proposed fault right-through strategies, the test scenario depicted in this slide was considered. It consists of a small medium voltage network connected to a strong power system through a circuit breaker. The medium voltage network consists of two smart transformers, a grid-tied and a grid-forming unit, each one with its own hybrid AC/DC low-voltage network. The presented parameters characterize each smart transformer and respective hybrid networks. In order to evaluate the fault right-through strategy for the grid-tied smart transformer, a three-phase fault was simulated in the test grid considering 10 scenarios, 5 fault impedance scenarios for a net generation scenario and for the load generation scenario. In this case, there is no disconnection of the small medium voltage grid from the main power system. Regarding the evaluation of the fault right-through strategy for the grid-forming smart transformer, two stages are considered. First, a three-phase fault is simulated in the upstream system, without disconnection of the small medium voltage grid from the main power system. After 400 milliseconds, with the fault still active, the medium voltage grid is disconnected from the main power system by opening the three-phase breaker in order to isolate the small medium voltage grid from the fault. In this case, the grid-forming smart transformer is expected to support the islanded operation of the small medium voltage grid without power interruption. Regarding the evaluation of the fault right-through strategy, both errors resulting from the simulated faults for the 10 considered scenarios are presented here, as well the considered fault impedances. In face of illustrated voltage sex, the proposed voltage the the effect of the proposal on the
Seems there are some problems.
Yeah, I think we had some problems with the playing back the video. I'm not sure if it's the video itself or with the transmission.
No, maybe the connection. I don't know.
Let's try and see if I can play it back from the version I have here.
You have a version. Is that I also have?
Yes.
But you can try. You can try.
I have to see that if I share my screen. Everybody is hearing the presentation, or
No sound. No sound actually.
just the video?
Just the videos.
limits of the medium voltage inverter.
And what about
okay.
now?
Sim. No, it's okay.
Okay.
The effect of the proposed fault right-through strategy on the active power in the hybrid distribution network for the considered scenarios is shown in this slide. The different contributions from the low voltage AC network and low voltage DC network are discriminated here. The discriminated contributions of load and generation existing in the hybrid distribution grid is also shown here. It is possible to observe that the most severe power curtailments are observed for the faults with lower impedance. Regarding the evaluation of the fault right-through strategy proposed for the grid-forming smart transformer, the main results are presented in this slide. Here we can observe the three-phase RMS voltage profiles in the medium voltage inverter of both smart transformers. During the voltage sag and islanding of the small medium voltage grid. The resulting RMS currents in the medium voltage inverters for both smart transformers in the formation moments is also shown. It is possible to observe that the grid-forming smart transformer can withstand the imposed voltage sag and perform a smooth transition to islanded mode after the isolation of the small medium voltage grid. This is made evident by the fact that the grid-tied smart transformer did not suffer any interruption. Looking into the detailed waveforms of voltages and currents in the medium voltage inverters during the fault start and islanding instant, the effectiveness of the proposed strategy becomes more evident. We can observe that the proposed fault right-through strategy can quickly adjust the output voltages and currents with considerably low distortion. Given this, we can conclude that the smart transformer can incorporate fault right-through strategies. By exploiting the voltage sensitivity of its hybrid AC-DC network, a grid-tied smart transformer without available local storage capacity can perform fault right-through and mitigate the adverse impacts of upstream voltage sags in its low-voltage hybrid AC-DC network. Also, by controlling the voltage drop in the inductance of the coupling filter of the medium voltage inverter, a grid-forming smart transformer can ride through voltage sags occurring in the upstream system and provide a smooth transition to an islanded operation of a small portion of the upstream medium voltage AC grid where the smart transformer is connected. The proposed fault right-through capabilities were evaluated considering balanced three-phase voltage sags. Further studies to evaluate the effectiveness of the proposed fault right-through strategies for balanced voltage sags are underway. And that's it. Thank you for your attention. Now I'm open to your questions.
Well, thank you for an interesting presentation.
You're welcome.
Just a quick, it's a small comment first. It's where did you implement your simulated model? You didn't present that. It was PSCAD and TDC, a real-time simulator.
It was in MATLAB Simulink.
Okay.
Exactly.
And if you have your presentation, it's can you show it to us? I have a question regarding the behavior of the voltage after the sag.
Yes, let me just see, how can I share my screen? Just a moment, please. Maybe you can tell me, because I'm a new user on this platform.
Okay, you see that after the sag, the voltage has a small droop, and I was wondering if you simulated longer times to see if it's not really steady failing down. Now we have it.
I figure out, yeah.
Go, I don't know the number of the slide, sorry for that.
The result, right?
Yeah, yes. If you see in this figure, yeah, you see that the phase voltage is starting to fall down. And it seems that they might have some, maybe some low frequency oscillations. And if you consider that you should be around 0.95 to assure that you have a ride-through capability, have you checked on that, or have you even considered that kind of problem?
I don't know if I understood your question. You are referring to low frequency oscillations?
Yes, you see there is some sort of a beating in the voltage.
Like here? Like here?
No, after that. Let's go to the right.
Here?
Yeah, this plot, just, let's see, around 0.6 seconds.
Ah, I see.
You see that the voltage has a droop.
Yes, I didn't show it here, but in fact there are oscillations. Yeah, they span for some seconds, actually.
Because if you
the
have
controller,
some, sensitive load, that might cause it to disconnect.
I didn't study that issue.
But maybe in the future, just
the oscillation actually is caused because by inertia emulation the controller has. So the load itself, it was modeled very simple. So no motors, no inertia in the loads, not that kind of stuff. So there are many possibilities that were not addressed in this paper.
Okay. Thank you so much.